Okay, so maybe we can get started. I think people are still joining, but we'll, I want to introduce our speaker for today. So I'm Monica Valluri. I'm one of the associate directors of MICDE. So welcome to our winter semester of the MICDE seminar series. So today it's my pleasure to introduce Professor Mark Vogelsberger. He is a professor at MIT. He got his PhD at the Max Planck Institute for Astrophysics in Munich, and then had an ITC postdoctoral fellowship at Harvard, followed by a Hubble postdoctoral fellowship at Harvard. For those who are not astronomers, the Hubble postdoctoral fellowship is one of the most prestigious fellowships in our field. He went on to become a professor at MIT an assistant professor at MIT in 2013, and has been there ever since. So he's also had numerous awards, including Alfred B. Sloan Foundation Research Fellowship. And in 2021, he received the Buchalter Cosmology Prize. He has, his research focuses on various aspects of cosmology, computational aspects of cosmology. He was one of the first to develop numerical methods to resolve what's called the fine-grained structure of dark matter, and make predictions of dark matter direct detection signals. He's one of the main architects and inventors of a large suite of simulations called the Illustris and the Illustris TNG project, which is extremely widely used by astronomers. And he has done simulations, is one of the first to do simulations of different species of dark matter called self-interacting dark matter and Bose-Einstein condensate dark matters. Today he's going to tell us about a new suite of simulations which looks at the earliest phase of the universe called re-ionization. So please join me in welcoming Mark to give us the seminar today. Thank you.
Okay. Yeah, thanks a lot, Monica, for this very, very kind intro. And really thanks a lot for having me, at least through Zoom. So I'm sorry that I cannot be there in person, but thank you very much for the invitation to present some of our recent work. So let me just directly dive in what we actually try to do in our work. So Monica mentioned already some aspects of that. So we are performing cosmological simulations. So that means we try to understand in a cosmological framework how structures and galaxies in the universe grow. So what you here see on this slide is kind of a history of the universe, starting with the very early phase of the Big Bang, and then all the various phases that we have now in this framework, like the inflationary phase. And then the recombination phase, where the first time when light was actually allowed to decouple from electrons and could freely move out. And this is also the earliest time where we can observe, at least in light, the universe, which led to the cosmic microwave background radiation. And then there are a couple of other phases in the universe. Most importantly, and for this talk, there's then this phase where the first stars and the first galaxies started to ionize the hydrogen and helium in the universe again. So that's called the epoch of re-ionization. And then we have these late times of galaxy formation, where then galaxies like the Milky Way, the solar system, and all the other things actually assembled. Now that's kind of the picture that we have for structure formation and galaxy formation. Now, if you want to study that and make theoretical predictions, you quickly realize that the equations become quickly very nonlinear. Yeah, so in these early phases, you can still linear perturbation theory, higher order linear perturbation theory, but at some point things become, in terms of, for example, the density contrast, which is shown here at the bottom, become very nonlinear. And the only way to solve the problem is really through numerical calculations. And this is what cosmological simulations are about. Over the last 2 or 3 decades, this field has really grown enormously. So there have been a lot of excellent groups, all over the world, also in Michigan, Chicago, and in many other places, where people have run these simulations with higher and higher precision, with more and more sophisticated algorithms, and also with more and more astrophysics actually included. And so this slide gives you a bit of an overview. So what you see here is different simulations indicated by their name. So this is not complete, but it just gives you an idea. And the simulations are split in various ways. So on the x-axis, they are split in so-called dark matter only simulations or in-body simulations, and hydrodynamical simulations, where we also include then the gas and stars and so on, whereas dark matter only, as the name says, only includes the dark components of the universe, so specifically dark matter and dark energy. Yeah, so these are simplified simulations that do not include helium, hydrogen, star formation, black holes, so none of that is included, but you only have the dark matter. And then on the y-axis, the plot here distinguishes between zoom and large volume simulations. So here the difference is that in large volume simulations, you simulate a certain patch of the universe with a uniform numerical resolution. And this patch has typically sizes of is a cube with a side length of typically a few hundred megaparsec, which translates to a couple of few hundred million light years. And the zoom simulations, on the other hand, are simulations where you focus all your computational power on a couple or one individual object. So for example, focusing all the computational power on simulating one individual galaxy. Now, the advantage of the zoom simulations, of course, you get this higher numerical resolution, so you can resolve more details in the galaxies. But the problem then is, of course, you lack statistics. So in these large volume simulations, you can these days simulate hundreds of thousands or millions of galaxies simultaneously in this patch. So this is kind of the landscape that we are dealing with at the moment. And so a lot of predictions have been made based on these simulations over the last 2 or 3 decades. Now, we also ran some of these simulations, as Monica already mentioned in the intro. So we have, for example, more recently finished this illustrious TNG simulation. So that's a simulation that actually consists of 3 volumes that you can see here: TNG 50, 100, and 300. So 50 megaparsec cube box, and 100 megaparsec and a 300 megaparsec. And what you see here is actually the dark matter density field. So you don't see any galaxies. So this is just at the present day the distribution of dark matter in the simulation and visualizing the density. And you see this cosmic web-like structure. Yeah, so these brighter spots here are so-called dark matter halos, where you have a lot of dark matter at high densities. And at the centers of these dark matter halos, you form then galaxies. And then you have these empty regions, these void-like regions, where you have a rather low dark matter density. Yeah? And everything is interconnected with this web. So this is a very generic prediction of these simulations. Now, one thing I would like to point out, because we always give these talks and show these results, is that this is really a multi-year, multi-people effort. So there's a lot of work going into that. So, for example, the model that I was showing you, this illustrious TNG, this goes back to work that we started in 2012-13, which because it takes a lot of time to develop the algorithms, to develop the physics that goes into that, and test all that. So it's really a quite lengthy process that also always requires a team of excellent people. Yeah? So it's kind of impossible to do this on your own. You really need to assemble a very good group of people that then work together on these projects. Now, just to give you an idea what these simulations can do these days. So this is a plot showing you the correlation of galaxies in the local universe. So at more or less the present time. So this is here measured in a so-called projected 2-point correlation function that is always shown on the y-axis, and the x-axis shows the projected separation. And this is here shown for different masses of galaxies, indicated here by this M star, which is the stellar mass of the galaxy. And the takeaway here is that the red line is the simulation prediction of this correlation function, and the black symbols are results from observations from the so-called Sloan Digital Sky Survey. And the main takeaway is that we get a reasonable agreement over this mass range in terms of this correlation. So this is something that, for example, if you have looked at this with earlier simulations, that was typically difficult to achieve to get this to this precision, actually. Likewise, you can also look at so-called luminosity functions. So this is shown here. So what these different panels show is at a given time in the universe, measured by the so-called redshift, you see the abundance of galaxies shown on the y-axis for different UV luminosities. So for different emissions, so to speak, in a certain filter. And again, the symbols here are data taken from the Hubble Space Telescope, mostly Hubble Space Telescope, and the lines give you an idea what the simulation predicts. And again, you see that at all these different cosmic epochs, the simulation is correctly predicting the abundance of these galaxies. So at different times, at different mass scales, so this works also remarkably well now. Now, the next frontier, both observationally and also theoretically, in terms of understanding galaxy formation, is the high redshift universe. So we have now a lot of high redshift observational facilities, like, for example, the James Webb Space Telescope, but also so-called 21 centimeter cosmology observations and probes, and many other things that specifically probe things like the epoch of re-ionization and earlier, to really go to the time where the first galaxies formed and the first galaxies assembled. So the focus, both observationally and theoretically, is now very much to understand onto understanding of these early phases of structure formation. And this is where this THESAN project becomes relevant. So this is a continuation of these simulations that I showed you before, specifically this illustrious TNG simulation, to really push predictions into this regime of the epoch of re-ionization. So that is something that we want to understand, because that is something that is very relevant for galaxy formation in general, but also for the state of the intergalactic medium, and so on and so forth. So that is the idea. Now, to model this epoch of re-ionization, you have to take into account radiation. So what you need is that for each individual star, for example, you need to track how the radiation propagates in your simulation and how it affects the various gas phases and the various components in your simulation. So that means specifically you generate your photons from the stars, and then they propagate outwards through the interstellar medium, which is the gas in the galaxies. Then it gets transmitted through the circumgalactic medium, which is the gas around the galaxies, all the way to the IGM, which is the intergalactic medium. And there it will then slowly start in a patchy way to re-ionize the universe. So if you want to understand the epoch of re-ionization, you have to model this photon emission, and or technically speaking, you have to do a radiative transfer in the simulation. Now, radiative transfer can be done in different ways. So I showed you illustrious TNG and all these other simulations in this overview slide. So all these simulations that I showed you did not include radiative transfer. So there's a good reason for that, because it's typically or generally very expensive to do radiative transfer. And if you want to have a simulation that you evolve all the way to the present day, it's computationally, at least at sufficient volumes and sufficient resolution, it's not feasible to do this with full radiative transfer. So all these simulations use a very simplistic model to model the impact of radiation. Specifically, they assume a uniform radiation field that does not specifically depend on individual sources. It's more like an average radiation field that is then evolved with time. So that's fine for these large volume simulations that mostly focus on the present day of galaxy formation and also on more massive galaxies. If you're interested in the epoch of re-ionization, the early sites of, or the early sources for re-ionization, and the faint end, also the faint end of the luminosity function, so the less massive galaxies, then you really have to take this radiation into account. And so there are different ways to do this. So what you see on the slide is one very popular approach where you essentially take your hydrodynamical simulation, like for example, Elastos TNG or any of these other simulations that I showed earlier before, and you just do the radiative transfer in a kind of post-processing way on a grid on top of this simulation. Yeah? So you have the density field of the gas, you know the composition of the gas, you know the radiative transfer equation, and you just solve this kind of in a post-processing step. Now, the advantage of that is very efficient, as you can do a lot of these calculations. The disadvantage is, on the other hand, that it's not self-consistent. Yeah? So it doesn't, for example, include any back reaction between the gas and the radiation, like the heating and so on and so forth. So all this is not self-consistently taken into account. So it has some limitations, but it's a great tool to do some parameter exploration. Now, if you want to go beyond that and really do kind of a full self-consistent simulation, taking into account the radiation as you solve, as the simulation progresses, and not doing this in a post-processing step, then you would need to take your hydrodynamical equations, so essentially in the simplest form, the Euler equations, and you need to couple this to the radiative transfer equation. And that leads then to so-called RHD simulations, so radiative hydrodynamic simulations. And they are then self-consistent, but the problem is they are computationally very expensive. Yeah, this has various reasons. One main limiting factor is the speed of light. Yeah, so the time stepping of the simulation will strongly depend on the speed of light because this is propagating so quickly. And so if the time steps become small, the overall simulation becomes slow. Yeah, so you have to just evolve slower. And so it's significantly more challenging to do these simulations compared to pure hydrodynamic simulations. So what you need is a quite efficient radiative transfer solver, and you also need a reasonably accurate model of the sources, where the sources of these photons are always the galaxies. Yeah, so the stars in the galaxies. So what you need is a realistic model for the stars as well. Otherwise, you have wrong sources and things won't work out. So this is exactly where THESAN comes in. So THESAN is one of these radiation hydrodynamic simulations that combines a galaxy formation model with radiative transfer to make predictions for the epoch of re-ionization. Yeah, and so for those of you who want to see some visual material like images or movies, please go to this website, because I won't have the time to show a lot of movies here in the talk, but you will find plenty of visualization material on this website. Now, THESAN has three key ingredients. One is the galaxy formation model, as I mentioned. So here we kind of use the Elastos TNG galaxy formation model that I mentioned before, because this is a very well tested and very accurate model that leads to a lot of predictions that are in agreement with observational data. But then on top of that, we also need a radiative transfer scheme. And here we use a rather simple radiative transfer scheme, which has the advantage that it's a very good compromise between efficiency and accuracy. Yeah, so you can write down more accurate radiative transfer schemes, but then they are typically slower. You can also write down less accurate ones, but then they are faster. So this is kind of a ideal situation here for this kind of scheme for the scales we are interested in. So what this allows you is to here specifically follow 3 frequency bins that you can indicate here. So these are exactly the frequency bins that are most relevant for this epoch of re-ionization calculations, specifically, for example, to ionize hydrogen. Yeah. Okay, and the third component that we also included that I haven't yet mentioned is that in the interstellar medium of galaxies, there's also a so-called cosmic dust component. So this is in terms of the mass budget rather subdominant, so only about around the % level. But this dust is very important in terms of its interaction with radiation and also for various processes in the interstellar medium that are indicated here on this slide. For example, you can have a lot of interactions with the dust and the gas, and also with, if you have supernova, this leads to changes in the dust, and the dust can also change its grain size distribution, which also means that its absorption features and cross-sections change. So there's a lot of physics here in the dust, and so we include a simple dust physics model that can track some of these processes as well. So it's 3 components, the galaxy formation model, the radiative transfer, and this dust component. So we put all this together, and let me just skip this. And then we run a large simulation comparable to this TNG 100 simulation that I mentioned before. So here's the volume of the simulation indicated. So it's close to 100 megaparsec cube. And then there are a couple of other numbers that indicate the resolution of the simulation. So what is the resolution in dark matter? What is the resolution in gas? And so on and so forth. And what you see on the left is then the output of this simulation at a redshift of 5.5, which is kind of the end of the re-ionization process. So everything is then nearly re-ionized again because of the radiation of the stars. And what you see on this slide here is all the different components that are included in the simulation. Yeah, so there's on the left, for example, the photon density field. Then on the upper left, there's the gas density field. On the upper right, the gas temperature field. And then there's on the right here, the so-called metal distribution. So this is everything that's heavier than helium is considered here metal, and this shows you the distribution of the density field of that, and likewise here's the density field of the dust. And on the lower left you see the H1 fraction. So this is the neutral hydrogen fraction. Yeah, so how much of hydrogen is still neutral? You see this is actually only neutral in these filaments here. Yeah, and I come back to this point a bit later in the talk. Then there are two insights also shown, which show a galaxy here at the center that you cannot see on the large scale view. So this is a significant zoom in here. And for this galaxy, two things are shown. One is a JWST mock image. So if you were to observe this galaxy with JWST, it would look something like that. And then there's also an ALMA mock image, which shows you how ALMA would see that galaxy for C2. Yeah. So this is just to give you an idea that, you know, on this large scale view, of course, you don't see the individual galaxies, but there's, you know, a lot of galaxies in that volume that are actually driving this re-ionization process. Okay. Now here are a couple of numbers on the simulation for those of you who are interested in the technical details. So the results, most of the results that I will show in the following are based on this THESAN 1 run. So this is kind of our flagship or production run. But then there's a couple of other simulations, like, for example, THESAN High, where we changed the parameterization of the so-called photon escape fraction in such a way that the photons mostly escape from massive galaxies, versus THESAN Low, where the photons mostly escape from low mass galaxies. Yeah, so the photons are produced in the stars. Yeah, the stars emit the photons, but not every photon makes it to the IGM because it can be absorbed before. Yeah, and so this is kind of to bracket the uncertainty in this absorption process. We have this THESAN High versus THESAN Low with this parameterization here. Then there's also a run called THESAN SDEO. So this is an alternative dark matter model that I will show one more slide on this to explain this a bit more. And then there are a couple of resolution test runs here at the bottom. Yeah. So that's kind of the simulations we have within the project at the moment. Now, just to give you a bit of a scope where we stand with this. So here on the right, this is an overview plot that has been generated by Dylan Nelson a couple of years ago, where he put a large number of existing hydrodynamical simulations in this space of, on the x-axis, number of resolved galaxies, and on the y-axis, the baryon mass resolution. And ideally, in this plot, if you want to push the boundaries to better and better simulations, you would like to go to the upper right. Yeah, so you would like to have a large number of resolved galaxies with a very high baryon mass resolution. Yeah, so this is exactly what you want. And you see where all these simulations actually lie in this space. Now on the left, there's a corresponding plot that Raoul Canan made. So this is not published, just using that for talks. And this is showing not hydrodynamical simulations, but this is showing a subset of radiation hydrodynamic simulations. Yeah, so simulations that include radiation. And on the x-axis here is the box size, so the volume that you cover in the simulation, and on the y-axis, it's again some resolution number. In this case, it's the minimum hydrocell size that you resolve in the simulation. Yeah, so the smaller that is, the better you resolve the hydrodynamics on small scales. And the first thing that you realize if you compare the two plots, there's a significantly lower number of radiative transfer simulations than hydro simulations. And this has exactly to do with the fact that it's just more expensive to run these simulations. Yeah. Now in this plot here on the left, you would like to go to the lower right corner to push for large volume and better resolution. And you can see how the different simulations do here. And so this is a very active field. So this, I'm sure this will be populated way more in the near future, but it's just more expensive to run these simulations. Good. I'm also mentioned this SDO run, this alternative dark matter run. Let me just say one word about this. So we ran the simulations for this SDO model, which is an alternative dark matter model, where you have at early times in the universe some collisionless damping of the power spectrum due to interactions between dark matter particles and some relativistic species that leads to these, as you can see in the red line, so-called dark acoustic oscillations. Yeah, so this is a specific particle physics model that is different, for example, from warm dark matter that you see here in the blue dashed line, which just leads to a cutoff without oscillations. And so we ran this just to understand what could be the impact of these oscillations. Yeah, so I don't have too many results on that model yet. So you will see it on a couple of slides as some line. But we are currently trying to contrast this against things like warm dark matter, and we also have now some fuzzy dark matter runs to see what the impact of these models is during the epoch of reionization. And that's a nice thing about these simulations, that you can just try all kind of alternative dark matter models and see how structure and galaxy formation or the epoch of reionization, how this is actually affected and how the early galaxy population is affected. Good, so let me show you some results from THESAN after giving you a brief overview what goes into that. So what you see here are light cones from the simulation. And what this is the dark matter density field and the gas density field, starting here on the left at redshift 16 and then going all the way to the end point of the simulation, redshift 5.5. And you can see here how structures are slowly evolving in terms of this cosmic web. Now, the more interesting plot to look at if you are interested in the epoch of reionization is then looking at the H2 fraction, how that evolves, and also the gas temperature. And what you see here is this nice patchy reionization process. Yeah, so you start with these first sources that start to re-ionize, and at the end of the day, if you're close to redshift 5.5, you have reionized essentially everything, and you have only H2 here. Yeah, and H1 went down significantly. Now, what is important in the modeling of this reionization process is not only that you get the radiative transfer more or less right, but that you also model the sources correctly. Yeah? So you want to model the photon sources correctly, because if you don't have these correctly modeled, then of course the whole radiative transfer has the wrong input, so to speak. And so we were particularly interested in having a model that gets the sources right. And this is also the reason why we use the TNG model as the underlying galaxy formation model, because we knew that the galaxy populations, as I mentioned and showed also in the beginning of the talk, are more or less in agreement with observational data, at least for the ranges of masses and redshifts where we can make some comparisons. Yeah. And so what you see here on this slide is kind of a diagnostic plot to check how well we are doing in terms of the galaxies and the masses of the galaxies. And so what you see here is the so-called stellar to halo mass relation plot. That means that you plot on the y-axis the ratio between stellar mass of a galaxy and the halo mass, which is mostly dominated by the dark matter mass. And you plot this as a function of the halo mass. And so there are some observationally or semi-observationally inferred constraints that you can see here in this blue band. And that's kind of a rough benchmark where you would like to end up. And then we also include here a couple of different simulations, and the black solid line is what THESAN predicts for this relation. And you can see, if you look at the different redshifts here, starting from redshift 6 to redshift 10, that the agreement is, it's not perfect, but it's reasonably good within the uncertainties of both the simulation and also this empirical modeling here. And so we are quite confident based on that plot that the galaxy population at these redshifts, which is relevant for driving reionization, is more or less in agreement with what we think, what we have in the real universe. And likewise, you can also look at the so-called galaxy stellar mass function that tells you for a given stellar mass of a galaxy, what is the abundance. And there are also some observations here available that you see here with these error bars. And the red solid line is again the THESAN prediction. And also here, if you look at the various redshifts, you see that we are mostly doing well. There are some discrepancies, but it's still more or less still within the error bars. Yeah, so it's not a model, but it's reasonably good. And for most of these comparisons, it's also quite a bit better than some of the comparison studies. So we are, again, kind of confident that the galaxies and so the sources of the radiation are modeled more or less correctly in the simulation. So that carries also on to other properties that you can check. For example, don't want to spend too much time on that slide, but you can check also, for example, the mass metallicity relation of gas in galaxies, which is shown here on the left. So there are also some rough observation constraints. So this is very challenging to measure that. So you get quite large error bars here, but also that is consistent. And then you can also make, for example, predictions of these metals and also the dust component in the various phases of galaxies. And so this is shown here on the right, splitting the gas phase metallicities and the dust component into a total component, then IgM, CGM, and ISM. And you can see that, of course, the dashed line here is the dust component. It's significantly less dust than the metals, but it's still, in some of these phases, still a significant contribution here. Okay, and the last plot to convince you that the galaxy population is more or less correctly modeled in the simulation is shown here. So this is a very busy plot here on the left, but this is similar to the galaxy stellar mass function plot that I showed you, but now focusing on UV luminosity functions and comparing this also directly to observations here. So the symbols here are the observations, and the lines are the simulation prediction. And by and large, this is also a pretty good agreement. You see here at the at the faint end, we have this kind of discrepancy here. So here, this is the regime where numerical effects are kicking in, and we don't resolve the faint end so well anymore. And you can see this particularly well if you look, for example, at this THESAN 2, which is a lower resolution version from the solid line, and you see that these are bending over earlier, and this is a pure numerical effect. Yeah. Now this bending over is also, you can also see this if you change the dark matter nature a bit. So if you look at the dotted line, so this is actually this SDO model that had this damping in the transfer function. And if you look at this at the matched resolution, so comparing THESAN 2 and THESAN SDO2, you see that this bends even stronger. So this is a physical effect that you see here, which is coming from this so this cutoff, this oscillatory cutoff that you get in the transfer function. So that's one, just to give an example, that's one of the impacts of changing the nature of dark matter, that you get this suppression at early times. And this is, of course, very well known, for example, for warm dark matter, but this is also something that you observe here in these SDO models. Now on the right, we don't focus on individual galaxies, but this is a so-called star formation rate density plot, where at a given redshift, you plot how much star formation in terms of solar masses per year there is in a given volume. And also, there are also some observation constraints on that. Of course, this doesn't go to these very high redshifts, because this is, again, difficult to measure. But over the redshift range where you see the symbols here, so there are some measurements with some error bars. And the red line is, again, the simulation prediction. And also here, the consensus is, okay, that this is a reasonably good agreement. So we, again, convinced ourselves that the galaxy population is kind of more or less in agreement with what we expect. Now, given all that, what I just showed is we are pretty confident that we can rely on, on the photon output. And so the next thing you can then check is the total ionizing emissivity. Now, this is shown for many different simulations here. So the red line is the flagship run, yeah, so the fiducial run, and then you can vary various things. For example, you can then look at these THESAN high and THESAN low, where, in THESAN high, we had the photons mostly escape from high mass systems, versus THESAN low, where the photons mostly escape from low mass systems. And you can see that this leads to quite strong differences compared to the red line. So, for example, the green one, this is leveling off towards lower redshifts, because then because of the hierarchical growth, you have more massive systems here, whereas THESAN high is very small here, the emissivity at high redshifts, because you don't have these massive systems yet, and it catches up towards lower redshifts. Yeah. Another thing that you see here is that the plot distinguishes actually the photon emission from stars and from AGN. So the AGN here are kind of subdominant compared to the stars, at least over that redshift range. Yeah, so this changes, of course, towards lower redshifts, but over that redshift range, the AGN contribution is really just at the couple of percent level compared to the emissivity of the stars. So these photons that are emitted will then eventually go to the IGM and lead to the re-ionization of the IGM. And this is something that you see then here on the left. So this is a very important plot for people interested in the epoch of re-ionization, because what it shows is, it shows you the neutral fraction of hydrogen specifically as a function of redshift. Yeah, and so we discussed in the beginning, or I mentioned in the beginning, the CMB. So this is when you get actually this neutral fraction to 1 again. Yeah, so everything is neutral. And then as the first stars are forming and the first galaxies, they emit the photons that we just had on the previous slide in terms of the emissivity, and they will then start turning the neutral hydrogen again into ionized hydrogen. And so the neutral fraction goes down. So also there are some observational constraints, sometimes upper limits, sometimes lower limits, and sometimes with error bars. But if you look at the THESAN 1 prediction, which is the red line, you see that's kind of broadly consistent with what we expect. So this favors actually here late re-ionization model, because we need to go to redshifts actually below 5.5 to get fully re-ionized in that model. Now, there's also a couple of other simulations shown. Again, THESAN high and THESAN low, these extreme models. And for THESAN high, for example, you see that because of the fact that we mostly let the photons only escape in high mass systems, so the universe stays longer neutral and then also goes down, versus THESAN low, where you let the photons primarily escape from low mass systems. So you get here an earlier re-ionization here. Yeah, and compared to the late re-ionization that we have here. And so these two models kind of are extreme cases in terms of re-ionization histories. And you can also see this if you look at the optical depth that is constrained from Planck, for example, that the green and the yellow here are kind of, borderline consistent, or more or less essentially actually inconsistent with Planck, whereas the red line, our, fiducial model, is kind of consistent here with the optical depth constraints. Yeah, so this is a kind of a broad overview of the re-ionization process as it is happening in the full volume. Now, the nice thing about THESAN is that you cannot only look at the full volume and at average quantities, but the resolution is high enough to also look at environments of individual systems. So this is visually shown here for 3 different systems, starting at redshift 9 to redshift 6, showing you the re-ionization process here for 3 different masses as indicated here. And what you see here is that, for example, there's these early stages where the ionization fronts are kind of stalling close to the sources because you still have rather quick absorption, but then once they hit low density gas, they propagate quicker. And then at these lower redshifts, you still have some neutral components left in the high density regime. So specifically these nodes of the cosmic web and the cosmic filaments have high enough density that they are not that they don't get ionized. Yeah, so there's a residual actually in the ionization fraction that comes from these higher density structures. And this can also be shown here. So this is showing you the ionization histories for different densities and how the different densities affect the time when re-ionization is happening. So these are the density cuts here in the legend, and the vertical lines always shows you the midpoint of re-ionization. And you can see that for high densities, this is around 8.2. So this is for this density contrast here. And towards lower densities, you push this actually redshift 7. Yeah, so it's not that it's not that re-ionization happens everywhere at the same time. So it depends in what kind of environment you are sitting when re-ionization is actually happening. And this also tells you that these standard hydrodynamical simulations, these simplistic ones that I mentioned before, where you have this uniform UV background that's just spatially uniform but time dependent, that's generally speaking not a good description of this process because there's a significant difference in terms of the re-ionization time for different environments. Now, a nice way to visualize that is if you take your gas density field and you color code by the re-ionization redshift, where the re-ionization redshift here is defined as the minimum redshift with a hydrogen ionization fraction greater or equal 99%. And then you get, again, a similar picture as what I described before, that you get this so-called inside-out reionization, and that the largest structures reionized first, and much later you get the low-density IgM. And the denser structures that you can see here in this embedded bluish regions, they stay neutral because of the density, as I mentioned before. And you can then also make these kind of maps for different models. So again, here's a comparison between THESAN low and high, where you have photons coming from low mass or high mass systems preferentially. And you can see that then THESAN low leads to this rather early reionization versus THESAN high, which leads to a significantly later reionization. One way to constrain then, or to study this reionization process, also observationally, is to look at these bubbles that are actually forming due to reionization. Yeah, so this patchy bubble-like reionization process. And there are different ways to quantify that. One way is to look at power spectra of the ionized hydrogen, which you see here. And you see here also in the color bar a mapping between the average H2 fraction and the redshift. And what you can see is, as you go from early times like redshift 9.5 here to lower redshifts, this distribution becomes broader and broader. So simply because these bubbles actually are expanding and become larger as galaxies also become bigger and the star formation rates increase. So there's a clear trend in this evolution of this power spectrum. Now you can also look at this in real space. So these are, for two different simulations, the bubble size distributions at a fixed ionization fraction that corresponds to a specific redshift. And comparing here the THESAN fiducial run, so you see all these borders of all these boundaries of the bubbles. And then THESAN high, again, where we let things only escape from larger systems. And you can clearly see that there's a quite significant difference in terms of the topology of the bubbles. And you can also look at this then at a different time to see the evolution, and you can see that also the evolution is then quite different in these systems. And so the takeaway here is that these bubble sizes, and a graduate student is currently working on that. These bubble sizes can actually really be used to constrain a lot of things on astrophysics and cosmology, like for example star formation rates, escape fractions, gas distributions, and so on and so forth, but also dark matter models. So if you have a cutoff in the power spectrum, as mentioned in the models before, then also the topology of the bubbles will be different between CDM, for example, and these alternative models. And just the last plot to show this here again in K-space. These are now bubble size distributions for different models at different H1 fractions here. And yeah, it's a very busy plot, but it's showing these 6 different simulations, and the trends are kind of what you would expect. For example, that THESAN SDO, this alternative dark matter model, if you look carefully at these power spectra, has a tendency to have larger bubbles simply because of the cutoff. Likewise, also THESAN high has typically more larger bubbles that you also saw in real space before, and THESAN low has typically smaller bubbles. So all of this is kind of imprinted here in this bubble size distribution, and so this makes this a kind of interesting thing to measure and to explore. Okay, just in the next 10 minutes, so I described kind of the core concepts and ideas and results of THESAN, but of course that's not the last steps. So we are currently working on some follow-up projects. So I don't have time to go very deep into that, so I just want to flash them and yeah, just give you the idea what this is about. So there are 2 projects I want to talk about, which are follow-ups, THESAN HR and THESAN Zoom. So THESAN HR is a project led by Josh Borrow. He's currently a postdoc at MIT. And the idea here is to take these large THESAN boxes, so they were 100 megaparsec cube, so they're quite large, to make them smaller, with the idea being that you can significantly better resolve the faint end. Yeah, so a lot of interesting things are happening at the faint end during the early phases of galaxy formation and also during the epoch of reionization. So these THESAN HR simulations are particularly tailored towards exploring the faint end. And you can see this here in this simulation table. So the box size of these, the lower two other THESAN HR runs are significantly smaller, as around 6 and 12 megaparsec side length. So really small boxes. But the advantage is that you can push then the mass resolution to more than an order of magnitude better than what you could do in the original THESAN run, and that allows you to resolve much smaller galaxies. And the idea of that paper that just came out recently on the archive is that you can then very specifically explore the impact of this patchy re-ionization on the early galaxy formation, because depending on what environment the galaxy sits in, the radiation fields can be quite different, and this impacts the overall evolution of the galaxy. And this is kind of shown here a bit on this plot here on the left. So the line that you see here that goes through the plot, so this is distinguishing two simulations actually. So one, as you can see on the lower left, with a uniform UV background. So this is kind of the model that standard hydrodynamical simulations assume, where you have this spatially uniform background that's just time dependent. And then the upper right, it's the full radiative transfer model that we used in THESAN. And so if you look at the gas temperature field, for example, which obviously plays some role for star formation efficiencies, because star formation happens typically in cold regions. So if you look at that, then you see kind of a super uniform temperature field in the uniform UVB run, because everything sees the same radiation. But it's very different in this THESAN run, where you get hotter and colder regions. And so depending now where your small galaxy is sitting, it will face a very different environment, and it will face a very different situation for star formation and other galaxy formation processes. So these questions are actually tackled in this paper. So for those of you who are interested in that, unfortunately I don't have time to talk about, please have a look there. So this is really particularly tailored towards the faint end. Then there's another project that we're currently working on that is not yet published, and that might also still take maybe half a year or a year to get published. So this is THESAN Zoom. So here, as the name indicates, is that we go away from these boxes and really focus on all the computational power on a few individual high redshift galaxies. And as I mentioned in the beginning of my talk, the advantage then is that you can resolve smaller details way better in these galaxies. And you can, among others, also resolve the interstellar medium and stellar feedback processes more reliably. And so what we do in this model is we actually use a completely different model for the interstellar medium and for the stellar feedback compared to what we have used in THESAN and also in Illustris TNG and many of these other simulations. So what we specifically use is the so-called Smuggle ISM model. The idea here is that it's a more explicit model in the sense that this model can actually resolve the various gas phases in the interstellar medium better than the old model that we used before. And I will show one or two slots about this in a second. And this gives you, and this is why we use it, this gives you, for example, the possibility also to resolve H2 regions way better than what we currently can do in THESAN with the old ISM model. And also, if you want to think about maybe going towards more self-consistent predictions for escape fractions, then this is also a step forward compared to the other model that we use that is too simplistic to answer these kind of questions. Now, let me show just a couple of comparisons between this newer model and the old model. So here you see an individual galaxy. It's the same galaxy on the left and the right, just simulated with different models for the interstellar medium. As from the left, there's this rough TNG model that we also used for THESAN, and on the right there's this more explicit and direct modeling Smuggle model, which resolve things in more detail. And what you see is a density field, or the gas density field of the two galaxies, and you can nicely visualize that. The left is really just a much more coarse-grained density field compared to the right, where you see a lot of fine-grained density fluctuations. And so this is because of this multi-phase structure of the gas that's resolved in the right model and not resolved in the left. And you can make this even clearer, this multi-phase structure, if you look at a phase plot showing number density of the gas versus temperature for the two models. And you see on the left, the gas is actually confined to a rather small portion of this phase space, and this is by construction. So the model has been constructed like that on purpose. But then this new model is very different. Yeah, so you have way more parts of the phase space being observed, being populated, and this is also consistent with what we think based on the observations what the ISM phase structure should look like. Yeah, so you will have very cold gas, you will have hot gas, and you will have a warm phase. And so you have a very rich phase structure that is correctly, or more or less correctly, described by this model. And to quantify this a bit more in detail, so these are two PDFs for the different phases of the gas. On the left is a mass PDF, on the right is a volume PDF, and then splitting the gas into a cold, warm, and hot component. And you can see that these three components, I mean, you see this in both panels, actually coexisting here. Yeah, so you get this this hot phase here, the cold phase, and the warm phase in both plots. And so this is again something that you could not do with the old model, because it would not be able to distinguish the various phases of the gas. Okay, and just a couple of other differences very briefly. You can also look at the so-called wind mass loading. So this is the stellar feedback in these galaxies is actually driving out some gas, and this is, for example, caused by supernova feedback or stellar winds or other processes. So there's some gas component that's driven out of the galaxies, and that can be measured in terms of this wind mass loading. And for a Milky Way-like galaxy, we expect that this should hover around 1. And so the galaxies that we are simulating here are similar to a Milky Way-like galaxy. And so the red line is actually showing the result, and you see that it's actually consistent with what we expect. So this is more or less to demonstrate that this driving from the feedback is consistent with our expectation in this more explicit model. And just another last quantitative plot on that. So you can also ask your question, how does the star formation rate evolve in these two models? And here on the left, this is a star formation history for the same galaxy that I showed you before. But now for the old model, this TNG model, which is called here SHO3. So you see that this is actually a very quiescent star formation rate. So you don't get a lot of bursts of star formation. It's more or less a constant line. And that's very different for the new model, where you get, where you see different resolution versions here from low, medium, and high that all show this bursty behavior. And this is a very generic prediction of all of these, more explicit models. So a lot of those have been developed over the last couple of years, and they all show this significantly more bursty behavior compared to this quiescent model here. So what this means is that the star formation actually works very differently. Yeah. Quiescent versus bursty, but then if you integrate the star formation rate to get the total stellar mass, which is shown here on the right, you actually see that all the models predict more or less the same stellar mass. So that means that the, like integrated quantities like the stellar mass of a galaxy are described more or less in the same way in the two models, but the way how you get there is very different. It's in one case you get there in a quiescent way, in the other case you have this very bursty behavior. Another takeaway from that plot is if you look at the different colors here, low, medium, and high, you see that this converges. Yeah, so you get converged stellar masses, and the numerical difference, I mean the mass resolution difference between low, medium, and high is each a factor of 10. So from low to high, it's a factor of 100. So if you change the mass resolution by a factor of 100, you still converge in terms of stellar mass. And so this is something that we were particularly careful about, that we can run this SMUGGLE model also in principle at resolutions that we can achieve in large volume simulations. Yeah, so the idea is to not only do a THESAN Zoom project, but then once we did that and we have all these Zoom simulations, then take a step back and then in the original THESAN run to also replace the ISM model with this new SMUGGLE model to make also their more refined predictions based on the ISM. And this gives us confidence that things should be converged also at the resolution that we can achieve with TNG or with this with the full volume, because the low resolution here is kind of matched to what we get in the large volume simulation. Okay, and just a very last slide before I come to my conclusions. So what you can then do, and what we did already, is you can take this SMUGGLE model, replace the old ISM model, and then do still the coupling to radiation and dust. and then do a very self-consistent calculation with this new model. Yeah? So what you see, for example, here on the left is then the emitted stellar light of such a galaxy, and you can see these fine-grained dust lanes. Yeah? So this is dust absorbing the light. You see also this bluish region. So these are star-forming regions where new stars are born, which are typically born, to be more in the bluish part, as you can see here in terms of the light. But then you can also look at this at different wavelengths. So here's again on the right, the optical, but then you can also look at the UV emission from the radiative transfer. And because we also have this dust component, we can also calculate the dust temperature then self-consistently and also get the IR emission from the dust. Yeah, so this is a general IR emission here. And so this is also a nice thing that we have these different components in one self-consistent model. Now, I should say that this is still isolated galaxy, so this is not a cosmological simulation yet, and it's also not a high redshift galaxy. The idea of THESAN Zoom is now to apply all this to high redshift galaxies picked from the THESAN volume to see how these galaxies would look like, taking all this into account that I just discussed. Okay, then let me come to my conclusion. So instead of showing a long conclusion slide, I just wanted to highlight a couple of other studies that came out along the THESAN project. So the top 3 entries here are all papers that came out in one batch when we published the first intro paper. So most of my plots came actually from this intro to the THESAN project paper by Raoul Canan, and the second one, Enrico Garaldi. Then Aaron Smith, for those of you interested in Lyme alpha emission, wrote a dedicated paper on that. And then there were a couple of other papers where we explored various aspects of the simulation, like multi-tracer line intensity mapping, but also a more detailed study on escape fractions and so on and so forth. So I just would like to encourage you to maybe go to the website and just look through this list, whether there's anything of interest for you. And I would also like to highlight that we would be super interested in any kind of collaboration. So if you have any idea how you could use the simulation, also just drop us a mail. We would be very happy to collaborate and give you access to the data to explore the simulation even more. And I will stop here. And sorry for going a bit over time. Thank you.
Thank you. So will you be able to take a few questions? I think we're
sure. Yeah, great. Yeah.
So in the astronomy department, we have this tradition of asking the graduate students first if they have any questions. So I'd like to call on any graduate students who are in the Zoom and followed by postdocs if they have questions. Please just unmute yourself or raise your hand and I'll. Okay, so no graduate students. Postdocs, any postdocs have any questions? Yes, David?
Hey, sorry, I just wanted to ask a quick question of when you were talking about the dust model that you're incorporating into these simulations. I guess I was curious if I saw you said on there scalar/live dust. So having looked a little bit at the dust modeling papers from your group, is the dust model that you're using here the scale? Is this the one with like a full size distribution of the dust grains, or just looking at the overall dust mass?
Thanks for the question. I'm sorry that I didn't mention that. So it's indeed there on the slide here. There are 2 dust models. The left that I have been describing is what we call a live dust model. In this case, the dust is modeled literally as particles in the simulation, and each of these particles carries an intrinsic grain size distribution that can be changed, for example, through these mass conserving processes like shattering and coagulation. So that's a particle-based model. Then there's also this scalar dust model. So this is a much simpler model where each computational cell just contains a passive scalar that is advected with a flow, and the passive scalar can be changed based on 2 governing equations which are these two equations that you can see here. So one of them is a growth and the other one is a destruction equation. Yeah, so the dust can go up or can go down. And the only thing that goes into this scalar dust model are timescales for the growth and for the destructions effectively in the terms of tau sh and tau sp. And what we are using in THESAN, so the large volume simulation, is the scalar dust model. Yeah, so we are only able to predict the overall dust abundance. Now, in the Zoom project that I mentioned towards the end, the idea is that we will then switch over to this live dust model because we have then higher resolution and also, you know, a better ISM model, so we have more confidence in actually making detailed predictions about the grain size distributions as well as it is provided by the live dust. So yeah, to summarize, on the large volume simulation, we use the scalar dust. On the small scale Zoom ones, we plan to use the live dust. Yeah.
All right, great, thank you.
Thank you. Yeah.
Any other questions from anybody else in the audience? Opening it up to everybody now. While people are thinking, I'll ask a quick question. I noticed that, you know, I thought it was really interesting that the S-DAO model that you had, the dark matter alternative, does seem to have a significant impact on the size of your bubbles. But it looked like there's also some degeneracy between the high and, you know, whether the radiation is coming out from high mass or low mass. And how do you think, I mean, do you think it's going to be possible to sort of resolve these degeneracies? And if so, how would you go about doing that?
Yeah, so that's a general problem of simulating alternative models. So not only for radiative transfer, but also if you do hydro simulations, like for example, if you do SIDM and you look at core formation, you know, this is also degenerate to some degree with supernova induced core formation. Yeah, and so we have the similar problem here. I guess, yeah, I don't have a good answer for the bubble sizes. There are some things that are different between, like, if you just look at you know, at the galaxy formation impact and the impact of alternative dark matter models. For example, if you think about SIDM, which is a variant of this, or SDO is a variant of SIDM, then you can show, for example, we had recently a PRL where we looked at the metallicity distribution in galaxies. And so if you have for example, a supernova-driven core formation compared to a SIDM-driven core formation, the metallicity structures in the galaxies are different. So we haven't yet thought about how this looks like in the bubble size distribution. So there might be things related to the timing, you know, when deviations in the bubble sizes come up. I think another way to think about it for the bubble sizes would also be if we had a more reliable model for the escape fractions, you know, that we could really trust, then this high-low parameterization, which essentially, you know, models the uncertainty in the actual escape fractions. If we had more knowledge and, you know, a better model for the escape fractions, then of course this degeneracy would go a bit away. But, you know, everybody working on that field knows that getting the escape fractions or having a good idea about the escape fractions is just generally very, very difficult. So there is this degeneracy between, yeah, the escape fractions and the SIDM. And as I said, one hope would be to reduce that degeneracy if we get a bit of a better understanding of the actual escape fractions in the systems. Yeah.
Okay, so I think we're a little over time, but I see some more questions. Gus, go ahead.
Great talk, beautiful work. I know we're over time, so I'll try to make this as quick as possible. I'm wondering, along with the other models extensions to this work, one possibility would be to take a volume that is overdense and, 100 megaparsec volume that is, say, 3 sigma overdense, and evolve that forward to get a look at the extreme environments that might be being probed right now by JWST, right, at a very high redshift. What are your thoughts on that? Yeah,
I think that's a great idea. I mean, we we just started with this simplest uniform box. So we have some plans also to studying, larger volumes, and then maybe also, doing what you just mentioned, also maybe focusing on some different environments. So we haven't yet started any concrete projects along these lines, but I think that would be interesting, especially because you saw this in the plots at the end. The overall radiation fields and so on are so sensitive to the overall density field, right? So get completely different results. Right. So having some tailored simulations of different density field, over density, lower densities, and so on, I think this would be computationally very interesting, and also it would be scientifically quite interesting to get these results for these specific environments, which we cannot probe at the moment because we don't sample them properly in the volume you have. Yeah. Right. So I think that's a great idea. Yeah.
Thanks.
Robert, I saw your hand up briefly, if you'd like to ask a last question.
Yeah.
Hi, Mark. I don't want to take too much time either, but I had just a few questions, and I'm not in this area, but I was curious, is the goal to compute an equilibrium, or do you also study transient?
Well, okay, this I have to put myself into that mindset. So there are some, we at the end of the day, like if you think about a dark matter halo, for example, right? So so the dark matter halos are these structures that are made of these dark matter particles. So they reach, if you push towards lower redshifts, when they kind of so-called virialize, they have a kind of equilibrium configuration. Yeah, but we don't. I think these systems don't achieve perfect equilibrium, and especially not in the simulation that we are running now, because we stop it at a pretty high redshift. Usually, there's still a lot of, in quotes, non-equilibrium processes going on in the dark matter field, and of course, this also applies to a lot of physical processes and the hydrodynamics. I'm not sure how to phrase the answer in the correct way. So there's always a significant contribution from non-equilibrium physics that actually goes into these calculations, and that's constantly happening, actually. Yeah.
Okay. I noticed also the number of particles is fixed in the calculation. Is that correct?
Yes. So let me just say 2 words about this. So the dark matter fluid is. The dark matter is modeled as a collisionless fluid using a Monte Carlo simulation with a fixed number of tracer particles, which is this particle number here, 2 times 2100 cube. But then the hydrodynamics is actually modeled with a grid-like code, and so these grid cells, they can merge and they can split. So there's a refinement scheme. So that varies a bit. Yeah. So we keep it also around the number of dark matter particles, but it can go up and down. So that's not fixed because the cell has like an AMR code, it has a refinement and a merging scheme incorporated, so that can fluctuate. But the dark matter particle or the dark matter tracer particles, this is a fixed number throughout the simulation. Yeah.
Okay, and maybe a last one. You mentioned about the time step being a restriction and with the speed of light, but given that, what is the most expensive part of the calculation?
Yeah, so the most expensive part, a large fraction goes actually to the hydro to solve the hydrodynamical equations. We do this in it's a standard Goodenough scheme, but this is a large fraction combined with all the physics. Like there's a lot of cooling going on of gas as well, and so the gas can reach quite high densities. So the hydrodynamics is quite substantial, but the radiative transfer is also quite expensive because we have to subcycle the radiative transfer because of the short time step. So there's one hydro step, and then there's a subcycling of RT steps, which can be, say 100 smaller time steps within a hydro step just for the RT. Yeah. And so the hydro and the RT are really the bulk of the calculation. So the gravity is not so dramatic anymore. If you have the hydro and the RT turned on, then the gravity becomes not so dominant anymore. But these are the 2 largest components. Now there are tricks to speed up the RT. So we don't have that yet, but there are other codes and from other groups that take the subcycling of the RT and outsource that to a GPU where you can do the subcycling way faster and then give the result back to the CPU. And then you can significantly speed up the radiative transfer. So especially on machines where you have large clusters of GPUs available, this is something that you can do to get rid of this bottleneck of the RT a bit. Yeah.
Okay, thank you very much.
Yeah, thank you for the question.
Okay, so yeah, let's again thank Mark for a really interesting and exciting talk, and we look forward to maybe welcoming you here sometime in person.
Yeah, thank you very much for the invitation again. Thank you. Yeah, thanks.